This work is the influence of sustainable reinforcing particulates on the density, hardness, and corrosion resistance of AA6063 matrix composites. This work is centered around reinforcing aluminium with sustainable materials and investigating the effect of these materials on certain properties such as the microstructure, density, porosity, hardness, and fabrication route stair casting. For this route, the fabrication parameters include melting temperature of 760 degrees Celsius, preheat temperature of the reinforcement of 400 degrees Celsius, preheat time for the reinforcement of 1 hour, stirring time of 10 minutes, and for the stirring, the two-step stirring method was adopted. The reinforcements selected were eggshell and fly ash. And in the case of the fly ash, it was used as is, while the eggshells were carbonized, and the carbonization was important to improve the carbon content and reduce moisture content, and also ensure adequate wettability. The abbreviation of the weight fractions were 2.5 for sample B, 5.0 for sample C, 7.5 for sample D, and 10 weight percent for sample E. Sample A was designated the. As stated earlier, the methodology, the microstructure was considered, and in the microstructure we are looking at the dispersal of the hybrid reinforcement and the presence of the defects. For the physical properties, we consider the density and porosity. For the mechanical properties, we consider just the hardness, while the corrosion resistance property we consider potential dynamic polarization. With the result of the microstructure, we could see that the reinforcements were uniformly dispersed in the aluminum matrix, and this was due to the employment of the two-step stirring technique. Also evident in the same micrographs for the reinforced samples was the presence of microvoids, and these microvoids were developed during the solidification of the cast. Agglomeration of the eggshells were also pertinent in the samples. Density showed that this property decreased with increasing weight fractions or the reinforcement, while the porosity increased with increasing weight fraction of the reinforcement. The increase in the porosity was due to the formation of entrapped air bubbles, which were present in the microstructure as microvoids. Analysis of the microhardness showed that it increased with increasing weight fraction of the reinforcement. This increase can be attributed to the presence of the hard reinforcing particles, which were dispersed along the grain boundaries of the aluminum matrix. This dispersal ensured the resistance to deformation of the samples during the application of the localized load. Another reason for the improvement in the microhardness with increasing weight fraction could be grain refinement. Lastly, the improvement in the microhardness was due to strengthening of the alloy. Now, the strengthening of the alloy occurs by the transfer of applied load from the ductile aluminum phase to the brittle and stiffer reinforcing particle. For the corrosion resistance experiment, the investigation showed that the improvement in the corrosion resistance of the reinforced samples was due to the formation of a sufficient passive oxide layer. It was also noted that upon further exposure of the samples to the corrosion mechanism, the passive oxide layer breaks down, and after that, corrosion initiation mechanism or corrosion mechanisms initiate. And then the major corrosion mechanism identified in this study was localized pitting. Now, as seen in the figure, the corrosion resistance for the reinforcement were way better than that of the base metal. Albeit the case, it was also seen that there was no direct pattern in terms of improved corrosion resistance for the reinforced samples, and factors that could be responsible for this include the weight fraction of the reinforcement, the level of dispersal, the presence of segregation and agglomeration, wettability, and interfacial bonding between the matrix and the. So in conclusion, this work was done to investigate the effect of Aluminium alloy 6063 reinforced with eggshells and fly ash. The work showed that the density decreased with the increasing weight fraction of the reinforcement, which suggests that the utilization of this hybrid reinforcement can produce lightweight aluminum matrix composites. The microstructure was characterized by uniformly dispersed particles, the porosity increasing weight fraction of both reinforcement. The microhardness improved up to 10.3%. Corrosion resistance was best for sample D, which was the 7.5 weight% sample. So it can be conclusively stated that the use of the hybrid reinforcement can produce AMCs with improved properties.